deliver his presentation. I will read short biography. Okay, Son Lampung is a professor at the School of Electrical, Computer, and Telecommunication Engineering, University of Wollongong. He received Bachelor Engineering with first class honors and PhD in Computer Engineering from Edith Cowan University, Australia. He was awarded the University Medal in 2000. His research is in the area of image and signal processing, pattern recognition, machine learning, and artificial intelligence. Now, he will present in image and signal processing, research and application part 2. Okay, I think time for you, Professor Lampung. Sorry, still mute.
Thank you, Dr. Pankan. Good afternoon, everyone. Selamat sore. Today, I'm going to give part 2 of my presentation on image process and signal processing, research and application. So it's just a quick recap of what we discussed last week. Our research lab conduct fundamental research and applied research. So in fundamental research, we investigate image processing, signal processing, machine learning, computer vision, and artificial intelligence, deep learning. And we apply our fundamental research onto real practical problem. So here are the list of 13 real-world practical problems that we have investigated. And in last week's presentation, I talked about the first 5 topics: assisted navigation for blind people, road scene analysis and self-driving cars, through one radar imaging, camera-based drone detection and classification, and age prediction from facial images. So today I'm going to talk for the 8 other projects. So the list includes drone imaging for precision agriculture, vessel surveillance using satellite imaging, naval mine detection with sonar imaging, multispectral imaging for biosecurity scanning, ground penetrating radar signal classification. And I also will talk about iris-based post-mortem identification and molecular analysis with atomic force microscopy, and finally functional magnetic resonance imaging image correction. So the first topic that I'm going to talk today is drone imaging for precision agriculture. And this is a research project that has been funded by the Australian Department of Foreign Affairs and Trade in the Innovation Partnership Grant. So in this project, we would like to use drone imaging in order to detect disease and pests on sugarcane farms. So for this project, we work with a sugarcane farming company in Vietnam, and this involved 4,800 farmer families, and they have 7,000 hectares farming land, and the company produced 5,000 tons of sugarcane plants every year, and it is the 5th largest producer of sugarcanes in Vietnam. So this video is a photo of their sugarcane farm taken from drone. So the sugarcane plants are affected by 4 common types of disease. So here we have Justi Lago minia or tanden. So it produced this black central leaf. The second type is called Procevus vonosatus, or so this type disease or pest, it eat inside the sugarcane plant and it produced it destroyed the sugarcane plant as in this photo. So the center part is eaten by the pest. The third type of sugarcane disease is called Ceratova cuna lanigera. So it has a lot of insect, like white insect like this, and it destroys the sugarcane leaf. And also the next one, let me look at the next one. The next one is called Cercospora longipi. So it is a type disease that affecting the sugarcane leaf, and when it's affected, the sugarcane leaf will have like dotted area like this. So all these four diseases will reduce the health and also the productivity of the sugarcane plant. So our job is to use sugarcane imaging in order to detect this disease and pest early, so that the farmer can apply treatments. So in this project, we use commercial drone like this to fly over the sugarcane farms, and the drone will take videos and images in real time, and then we process those images and video in order to detect sugarcane disease and pests. And the drone can be fly autonomously. So this video shows the autonomous drone. On the left-hand side, we program the drone to fly according to this yellow path, and the drone location is shown in the red dot here. And then also the GPS location of the drone is shown at the top. And on the right-hand side, we can see the image captures by drone at that particular location. Okay. So by performing disease and pest detection on image, we can translate it to the real world GPS coordinate. So this video is the result of weed detection. Besides disease and pest, weed is also a common factor that affect sugarcane plants. So by detecting weeds, then the farmer can automatically apply chemical to remove the weeds. So in this video, the detected weed area is shown in the red rectangle, and also we made the weed area for a particular image, for example, 5.91%. When the density of the weed or the percentage of the weed area is very large, it means that that area needs to be treated. So this video is taken directly from the drone. And our next task is to detect the 4 type disease that I mentioned earlier. 4 type disease that I mentioned earlier. So they are color coded. So the first disease is this pink color. The second disease is coded as yellow color. The third disease coded as blue color, and the last disease coded as red color. And in here, for example, in this given image, we detect this Cercospora we detect Eustilago city Taminia. So as this blue rectangle, and the confidence score is 0.82 or 82%. Yeah, so I played the video for only very short time. So after we detect the disease in the image space, what can we do next? So showing on the bottom left-hand side is the width map produced by our AI tool. So so you can see the trajectory that the drone is flying over, and then we coded each drone position as with color, where if there is a red color, that means that the width density at that location is very high. But if there is a yellow color, that means the width density at that location is medium or low. So it means that at those red location, we need to apply chemical to remove the width. So this width map can be fitted to another drone. So showing here is a footage of DJI agriculture drone called T20. This drone can carry up to several kilograms of water and chemical and liquid, and it can be used to spray fertilizers, pesticide, or weed killer. So this is a video of the agriculture drone that applying on the sugarcane farm in Vietnam in our project. Yeah, so we can use this one to spray fertilizer or pesticide or weed killers, or also fungicide to treat the disease. So this drone, all it requires is a map of the wheat or sugarcane disease. Um, and we have deployed our AI tools, and this is a photo taken during the technology demonstration day in November last year. So it had representative from the Australian embassy to Vietnam, and then also Vietnamese government official. And here are some of the drones that we use, including Mavic 3 and Phantom 3 drones. Can you listen to my audio so far? Yes. And you can also see the screen share, right? Yeah, thank you. Yeah. So I'm going to talk next another project. It's called Vessel Surveillance with Satellite Imaging. And this is a research project funded by the Australian Geospatial Intelligence Organization and Frontier SI, Ageo Analytic Labs. So we conduct this research from 2021 to until this year. So what is the aim of this research? In this research, we aim to develop AI tools to analyze commercial satellite data and detect vessel and classify vessel. And this is used to provide maritime domain awareness. For example, here is an input synthetic aperture radar image, and we need to develop AI tool in order to detect the location of every vessel in this image. And then for each detected vessel, we also further classify into different categories. For example, cargo ship, fishing ship, military ship, and so on. So very soon I'm going to show you 4 AI tools that we have developed. So the first AI tool is able to detect all the vessels from satellite optical image and video. So in this demo, every detected vessel is shown in the green color with the confidence score. So the confidence score is between 0 and 1. 1 means highest confidence, 0 means very low confidence. So we apply this tool on the satellite video obtained near Singapore and also some other location as well. So you can see it can detect onshore vessel. So what is the possible application of this tool? By using this tool, we will be able to detect vessels at sea for search and rescue mission. And we don't make any distinction between military vessel or civilian vessel. We detect all the vessels. Yeah. So and so this is a test of our tool in Hong Kong, China, in the port of Hong Kong, China. And we also test our tools in the port of Busan in South Korea. So you can see that in this port there are so many vessels and they are very dense. They stay very close to each other. But our tool are also able to detect the vessel very accurately. So so far we can detect all the vessel, and next we produce a tool that can detect and differentiate between civilian vessel and military vessel. So a civilian vessel is represented as a green box and green tag, and a military vessel is encoded as a red box and red tags. So by detecting a vessel as a military vessel, it means that it may trigger further analysis from the government officials. So we apply this one in some port in the UK, and here you can see it can detect carrier, ship, destroyer, and so on, and many other type military vessels. Okay. So this tool basically try to differentiate between civilian vessel and military vessels. So we test our tool also in the Norfolk Naval Station in the US. So the third tool is that so far tool 1 can detect all the vessel. Tool 2 can detect and differentiate between military and civilian vessel. So for tool 3, we actually classify subcategory of military vessel. So there are seven category: aircraft carrier in green color, landing in red color, cruiser in blue color, destroyer in purple color, frigate in cyan color, patrol in magenta color, and submarine in dark purple color. So we test it in several naval bases in the US. So here you can see we can detect a lot of submarines, very large aircraft carriers, and so on. So far, in Toon 3, we detect the military vessel and represent it as a square or rectangular bounding box. But in Toon 4, we actually also determine the precise boundary of the vessel. For example, here we detect a destroyer and we have the rectangular bounding box, But then we also have the detailed boundary of the vessel, and we also can estimate the length and the width of the vessel. For example, for this vessel here, the length is 176 meter and the width is 23 meter, and also for other vessels as well. So what is the possible application of this tool? Suppose that we have a very large area, for example, the Yokosuka area in Japan. This area have, this region have an area about 4 kilometer by 5 kilometer. It's very large, cannot be covered in a single satellite image. So what we do, we write automatic code to obtain several satellite image slices for this region. And for each region, for each satellite slices, we apply the AI tool and perform the detection. And after that, we collect all, combine all the detection results to produce an output map that look like this. So in this output map, every dot is a detected military vessel. And when we click on a dot, then we can find further information about that. For example, this one here, the dot here, that means the vessel is a destroyer at this given GPS coordinate. And if we click on the green dot, it is a aircraft carrier at the given GPS coordinate. And if we click on purple dot, it is a submarine at the given GPS coordinate. So that is some very brief description of this work. So the next project I would like to discuss is naval mine detection using sonar imaging. So this research project has been supported by Defense Innovation Network. So we know that naval mines are very cheap, easy to deploy, and very effective in asymmetrical warfare, and it's usually used to block shipping lanes or maritime routes. And statistics have said that since the end of World War II, naval mines have sunk or damaged more ships than all other type of weapons combined. So this research aims to detect underwater mines using sonar imaging. And on the right-hand side, you can see some photos of naval mines. So in this project, we use the autonomous underwater vehicle with sonar to scan the seabed. And there are several autonomous under vehicle, say Remus 100, Remus 600, Gavia. And they are actually very expensive equipment. They can cost up to $1 million. So here is photo of a Remus autonomous underwater vehicle. So it has propulsion steering, it has GPS locator and Wi-Fi antenna to communicate with mothership. But then most importantly, it has a side scan sonar operating at frequency between about 900 kilohertz and a range of 30 to 50 meter. So how does this device work? This is video footage from public domain. So this is how the Remus is deployed. And on the side, you can see the side scan sonar. So how does a sonar image is formed? So this video illustrates how the AUV travel. So when the AUV travel, it will send beam of ultrasonic signal, ultrasound. So the ultrasound, when it hit the seabed floor or any target, it will be reflected back. And then by collecting the reflected signal, this sonar will form an image of the seabed floor line by line. So in this research, our job is to take the sonar image and then detect the naval mine location. So here's the results of our algorithm. So the red box, in each image, the red rectangle is a location of naval mine with a confidence score, and we published this research in IEEE Access in 2020. So if you want further information about this research, you can find it in the public domain here. So not only detecting naval mine, we can also find a lot of information about the seabed floor from the sonar image. For example, on the left-hand side is a sonar image, and then on the right-hand side, we label every pixel automatically into 6 categories. The first category is MLO, or mine-like object, red in red color. The second category is sand ripple, the cyan color. The third category is yellow, or representing rock, and then blue color representing sand, and then black color represent other class, and the green color mean nadir. So nadir mean, the word nadir in English mean below. That is the area directly beneath the autonomous underwater vehicle. Yeah. So besides developing the software tools, we also deployed it on a portable GPU computer. So in this case here, we deploy our algorithm on the NVIDIA Jetson Nano, this small device here. So it can operate at very low power, only 5 volt, 4 ampere, and it had very small size, only between 7 centimeter and 4.5 centimeter. And then we also connected this NVIDIA Jetson to a monitor for displaying, and it also can be connected to keyboard and mouse for input. So this is just zoom out in photo of the NVIDIA Jetson Nano. That means our entire AI tool can be deployed on this portable device. I hope you are able to follow my explanation so far. So I'm going to talk next about another research project. It's on multispectral imaging for biosecurity scanning. And this is a research project funded by a company and also the New South Wales government in Australia. So the company is Intelligent System Design. So you know that Australian conduct 90% of its trade through seaport, and the seaport handle about 1.2 billion dollar worth of goods and goods every day. And on average, each day there are about 22,000 shipping containers like this arrive at Australian seaport. And this shipping container can carry a lot of biosecurity risk. And according to the report by government, those biosecurity risks, including pests and contaminant, cause damage worth about 4.6 billion Australian dollars per year. And because of that, shipping containers are inspected for biosecurity risks when they arrive into Australia. And people usually use manual inspection, X-ray, or detector dog. So in this research, we would like to investigate new technologies based on multispectral imaging to detect biosecurity risks. And on the top, you can see several examples of biosecurity risks, including invasive pests, invasive plants. So in this project, we use a multispectral camera, CMIA, just with the photo showing here, and it captured 25 bands of image, and it covered the wavelength from 664 nanometer to 950 nanometer, and it produced an image of 409 pixel by 217 pixel, and the size very small. The camera size about 7 centimeter in length. So what type data this camera captured? Showing here is a video of 25 bands captured by this camera. So the band are number 1 over 25, 2 over 25, up to 25 over 25. So for each band, we see the wavelength. For example, for band 8, the wavelength is 753 nanometer, and the image capture is given here. So here we have band 1, band 2, band 3, 4, and so on. So each band corresponds to one particular wavelength. So by knowing the image, we can know more information about the material of the object. So unlike the normal camera such as in your mobile phone, it captures an image that have 3 color bands, red, green, and blue. This multispectral camera captures 25 bands. So we have 25 bands, and if we select 3 bands, we can form an artificial color image. For example, from the above 25 band, I combine 3 bands at the band 1 and band in the middle, and then band 25. I can form an artificial color image like this. And in this image, you can see there are soil, there is metal, there is plant leaf, and there is some insect. So the difference between this multispectral camera and the color camera is that now every pixel has 25 spectral value. So showing here is you can see there are for each pixel there will be 25 value plotted as a curve, and then the vertical axis is the spectral value or the intensity value, and the horizontal is the wavelength or the band. So we have band 1, band 2, up to band 25. So in this plot, there are 5 class of material of interest. Green color is for plant, blue color is for soil, red color for pests or living creatures, and then the yellow color for metal. So by looking at the spectral curve, we will be able to differentiate between different type of object material. But then we are not going to classify each spectral curve pixel by pixel. We actually process the entire image directly. So to do that, we need to build a label image dataset. So this label image dataset have about 4,625 images, and each image have width, height, and 25 spectral band. So here the top row is the artificial color image for, and then the second row is the segmentation ground truth, where we have 5 type objects: yellow for metal, red for creatures like pests and insect, and then blue for soil, and then we have green color for plant or leaf, and then we have black color for background. So from this label data, we can train deep neural network algorithm to segment the multispectral image directly. So here is some example of how, so here, on the left hand side is the artificial color image describing the scene. So the input image to the network is actually 25 band image. And then the middle image is the ground truth segmentation results, where there are 5 categories: blue for soil, yellow for metal, green for plant, red for pest. And then the right hand side is the results of our AI algorithm. And here you can see it segmented the scene automatically into um, 5 category: metal, plant, pest, and soil. So, for example, this metal corresponds to the shipping container, and then the green color mean plant, red color mean pest. So whenever we detect plant or pest on a shipping container background, it means that this is a biosecurity risk. So besides developing the tool for industry partner, we also published our research in 2 journal articles, one in attribute transaction on circuit and system for video technology this year, and one on neurocomputing last year. And you can refer to our research paper for more information about this research. So this is the final system that we built. So it is based on NVIDIA Jetson Xavier, and it's connected to a... So ground penetrating radar is very useful for surveying the object underground. So in here we use ground penetrating radar to study the object or the rail ballast under the rail track. So in this video, we put the ground penetrating radar device here on a car, and we slide the car over the rail track. So that way, then we can obtain ground penetrating radar signal from object under the ground and classify those type of objects. Yeah, so this is a cross section of a rail track. So at the top we have the rail metal bar, and then sitting on slipper. Slipper usually is made by concrete, or in some case it's like very hard good. Underneath it we have ballast. Ballast is just contain a very small rock, and they are used to stabilize the rail track. And underneath it we have soil and natural ground. So the ballast is very important for the stability of the rail track. So when the ballast is in good condition, we have stable rail track. But when the ballasts are not in good condition, then the rail track is not operating very stably, and it may cause accident. So in here, here is the on the left hand side, we have the ground penetrating radar signal obtained for the region beneath the rail track. And then our job is to develop machine learning algorithm to classify this GPR signal. In here we have 3 categories. The middle category called clean, that means the ballast is in good condition. And then the other is with clay and with coal, when the ballasts are contaminated with clay or with coal. So it is a one-dimensional time series signal classification problem. So we developed several algorithms for this, and we have published it in 3 attribute journal paper. One is 2 on attribute transaction on geoscience and remote sensing, and one on attribute journal of selected topic in remote sensing. And we can process the signal not only in time domain, but also in frequency domain. So next, I'm going to talk about molecular analysis with atomic force microscopy. So this is a research project that funded by the University of Wollongong and the major equipment grant. So what is atomic force microscopy? It's a type of imaging that is specialized for very tiny objects or tiny particles. So here is a photo of the atomic force microscopy scanner at the University of Wollongong, and it is produced by a Japanese company, and it costs about 300,000 Australian dollars. So the idea of this atomic force microscopy is shown on the right hand side. Suppose that we have a very small molecule that we want to obtain an image. Then we put it on a sample surface, and the sample surface is put on a scanner, and this scanner have a robotic platform allowing it to move under this cantilever and tip. So for the atomic force microscopy, we shine a laser at the and then when the laser hit the cantilever and tip, it hit the sample surface, and then it reflected back, and the reflected laser is captured by a photodiode, and then feed to the detector, feedback and electronic. That's why then we can form a atomic force microscopy image. So here is an example of the video captured by this atomic force microscopy image. So in the image on the left hand side, every pixel have a size of 20 nanometer by 20 nanometer, very small. Okay. So in this project, our job is to segment the molecule and measure the size and also the shape of the molecule. So so on the left hand side, the input video captured by atomic force microscopy scanner, and on the right hand side is the results of our image processing algorithm. We segmented individual molecule and we named them molecule 1, 2, 3 up to 9 and so on. And for each molecule, we measure the perimeter, the area, the orientation, the circular measure, the eccentricity measure, and so on. So we published this research in Journal of Molecular Biology in 2019. So in this case here, it's very easy to segment the individual molecule because the background is very smooth and simple, and the foreground, the molecule, is quite visible. But in reality, the background is actually extremely complex, just like this. So using color information or intensity information alone is not enough. We actually need to measure the motion, the molecule movement between video frame. So for that, we developed a tool in MATLAB, and this tool uses segmented object by using the optical flow. So we first of all compute the optical flow for the AFM video, and then after that we threshold the optical flow, the motion, and then detect the moving object. So that is the only effective way that we can segment the molecule from very complex background. So I'm going to talk about our last two projects. One is iris-based postmortem identification. So this is a project funded by the Office of National Intelligence and Defense Science Technology Group under the AI for Decision Making Initiative. So the interest in this project is to be able to recognize or identify deceased people who die. So some just a bit of warning, some of the images that I show you next are the iris scan of dead people. So the image can be a bit disturbing. So so given when a person dies, then we can take a scan of their iris and we can recognize the identity of the person. So for this, we need to perform two tasks. The first task is iris segmentation. That means segmenting the iris region of the eye, and after that we perform iris recognition. So the middle image is how we segmented the iris region indicated by the blue, green color, and after that we apply the classification algorithm to identify the ID of the person. So in order to segment the iris region automatically, we use a deep neural network for semantic segmentation. So to train the deep neural network, we need to produce training data, label data. So given an image, we manually
Recording in progress.
diagnostic. So you know that functional MRI has been used a lot to study the human brain. So for example, on the left-hand side is a photo of a CMN 7T magnetome scanner at Center for Advanced Imaging, University of Queensland, one of our collaborator. So we use this one to obtain the data for this research. So on the right-hand side is a brain image obtained by this functional MRI. And this is only one slide of the human brain. And there will be several slides like this. And when we obtain the image, we can obtain using two encoding direction. One is from left to right and the other from right to left. And the problem is that because the brain tissue reflect differently to the electromagnetic signal, so it creates distortion, and the distortion depends on the direction of the encoding from right to left or left to right. So in here, for example, you can see we have exactly the same human brain, but depending on the left to right scanning or right to left scanning, we could have slightly different functional MRI image. And if we need to analyze this functional MRI image correctly, we need to correct for those artifacts in the functional MRI. So for that, we developed two algorithms, and we published it in two journals, Magnetic Resonance Imaging in 2020 and Journal of Neuroscience Method in 2020. So our tool take the two input FI functional MRI image, I1 from right to left and I2 from left to right, and then it also take one reference anatomy image. It's called T1W. It's called input A, and then it will produce two output images, E1 and E2 for the two input I1 and I2. So if you compare the input image and the two output image, and then you can see that the two output images have less distortion, and also our two output image align very well with the reference anatomy image. So this output of our algorithm can be used to improve the processing of functional MRI image of the human brain. So I have reached the end of my presentation for today. So just to summarize, I talked for Today I explain 8 different projects from number 6 to number 13. So if you have any question, you're welcome to ask me.
Okay, thank you very much, Professor Sang. This very interesting presentation. Okay, for audience, any question? Maybe from me,
Yeah.
Professor Sang. This is very interesting. I will ask about your topic about drone imaging for precision agriculture.
Yeah.
For the drone, actually, uh, what the height the drone?
Yeah.
That's the first question. What the
Yeah.
height? And the second, how fast? How
Yeah.
fast the drone? The velocity.
Yeah.
Velocity. And
Yeah.
then this very, and then maybe you can explain about the image processing. Yeah, I mean the pre-processing, the pre-processing about the image. Yeah.
Yeah. Okay. Yeah. Thank you very much for the question. Actually, this project, drone imaging for precision agriculture, it have a lot of interest now in Australia and also other countries. People start applying drone technology for agriculture. So for the question, say, how high the drone should fly, right? That one depending on the application. If you only try to detect like large object, you can fly the drone very high. For example, detecting tree, forest. But if you want to detect disease, then the image you need to fly the drone quite low. So um, so in our case, we fly the drone at about distance about 3 meters above the plant. Because if too high, then the image resolution is not good enough. Like that. So for example here, you can see here that this is the one that we fly the drone at about between 1.5 to 3 meter above the sugarcane plant. So that's why then we can see individual leaf and detect disease and so on. Yeah. And the next question is how fast we should fly the drone, right? So usually the drone can fly very fast, but for in this case, for this example, we fly probably at the speed of about 1 meter per second, so that we when we construct the map, like for example, I show here, when we construct the map, so this is the typical flying scanning speed of our drone. Yeah. So the distance is about between about 1 meter per second, approximately. Yeah. But if you take individual photo, then you probably have to fly the drone very slowly. But if you take continuous video, then you can afford to fly the drone faster, because in 1 second you will have 25 video frames, and then you don't need to use all of that. Yeah. So for your next question is post processing, right? Yeah, post processing the image, right? So post processing or pre processing the image. So usually for this project here, when we obtain the image like this, we just apply the AI tool directly on the image. So that means even our AI tool can cater for different lighting condition and so on, because we collect data from different lighting conditions. So we don't need to have so much pre-processing in that sense, in AI sense. But there will be need in pre-processing for building the map. For example, when we fly the drone like that, we have a lot of video, image and video like that. And to construct this with map, then we need to stick the image together into like, for example, this one here. When we fly like that, you can see that every time we we take only one section of the farm, and we need to stick them together to form a big image of the farm. Yeah, so that is very useful pre-processing, and there are two ways to do it. One way is we can do it ourselves by writing the code, stick image together, but then drone companies such as DJI, they already have tool to do that. So that means the company, the manufacturer of drones, they provide tools that can pre-process, and you can fit, the tool is called DJI Terra. So you can, it can allow you to stick on these image captures at a different point to form a bigger image of the farm. Yeah, and by that, after that, you apply the AI tool, it can produce this map. Our tool can produce this map directly. Yeah. So that means, to summarize my answer to your question about pre-processing, if you use existing tool provided by drone manufacturer, it can make pre-processing tasks very simple. It allows you to focus more on the AI image processing aspect.
Okay, thank you very much for your explanation. Okay, any question from audience? Ada pertanyaan? Silakan. Yeah, actually, just yeah, okay.
Yeah. Go ahead, please. Yeah. Go ahead, please. Any question is welcome. Let me increase my volume a bit. So yeah, okay. Go ahead, please. Yeah. Uh, so far, um, so far, this system is not deployed on Amazon Web Service. So we actually run it on our own computer. Yeah. So yeah, that's fine. Yeah. So this tool we work with the Australian Defence. So we have set permission to share some of the information in public like that, but a lot of detail, um, but I haven't discussed in here. Yeah. 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 Thanks for the question.
Okay, thank you for question and explanation. Oke, ada lagi pertanyaan? Any more question? Pak Iwan mungkin mau bertanya, silakan. Ada lagi yang mau bertanya? Ya, oke. Okay. Yeah, actually now we have maybe what's your comment? Yeah, what's your comment? Because now we have the the current detection is YOLO.
Hmm.
And what's your comment? I mean, what's the challenge? What's the challenge if we get YOLO and the challenge for the next research?
Okay. Yeah. Thanks for the question. I think your question is very significant because we know that nowadays there are so many existing tools for detection, right? For example, YOLO version 7, YOLO version 8, YOLO version 5, right. So what are the research challenge? What else do we need to do, right? What else do we need to do? Because there are public tools that everyone can use, right? But It's only when you apply those public tune to real problem, you start realizing that they are not perfect. That means in terms of accuracy, if we want to push it to commercial or defense or security application, then the accuracy is not sufficient. So we should always try to improve accuracy and robustness of the tool. Actually, so to improve accuracy, we can tackle it from two aspects. One is practical engineering. That means you design, prepare data, label data better. You train the system and find parameter that is more suitable. So that's why hopefully you can create better system than the public. Yeah. So that's from engineering perspective, and that require a lot of try and error and investigation. So the second part is also developing new algorithm, because even the best tool like Jodo version 8, we realize that when we apply it to some problem, for example, road defect detection or disease and plant detection, they still make a lot of error. Yeah, that means the research problem is not fully solved yet. There are ways that people should develop new algorithm, better way for the practical application. So a lot of our fighting is only confirmed when we apply the tool to real problem. Yeah. So to so just to summarize our question is that that means even with the very quick, very advancement in say Jolo, when we applied it to real problem, we discover that it still make errors and it still need to be improved. And yet, from my point of view, it has two ways we can improve it. One is engineering practice, by selecting model better, preparing better data, evaluate model, train the model better way. The second part is also in terms of to improve is conduct research, developing new, better algorithm, faster and then more reliable. Yeah, 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 sure. Go ahead. Yeah, 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 yeah. Okay. Yeah, yeah. Okay. Yeah. Thanks for the question, because my team also face very similar question, similar problem. For example, when we try to detect road defect, for example, like this. So when we try to detect road defect classifiers, so when we have a object detection application or problem like that, first of all, we think of say we need to prepare label data, right? So that means the input image and then the location and the type of the object. For example, car, people, bicycle, or the type road defect, like this. Yeah, and uh, and so we need to first of all prepare data first. Yeah. So we prepare the data first. So after that, we need to think, say, how we should partition the data. So we will have some data for training, some data for validation to prevent overfitting, and some data for testing. Right? And in the next step, we need to answer a lot of engineering questions. For example, what the input size that we should fit to the network? Is the image size 640 by 640, 960 by 960, or so on? So for different input image size to the network, there will be different in performance. So you need to identify which is the optimum image size. Yeah. So that is only one parameter. So the next one we should say is what the backbone that we should use. For example, for the detection network, let's take say YOLO version 8. It has tiny backbone. It has medium backbone, small backbone, large backbone, and extra large backbone, and so on. So after conduct the experiment, we can identify for this particular problem, which backbone is most suitable. Yeah. So after that, we still need to ask the question, say, what the batch size? The question that you had last week, say, should we use batch size 1, 2, 3, 4, 5, 8, and so on? So there you need to consider also your GPU power and also to analyze the most suitable batch size to train the network. So you can also think of many other parts, say the number of layers and also the connection between the layer. So the more you go to it, is the more we go towards the research side. Yeah. So that means to designing a effective detector like that. So a lot of our detector system, it has been after we develop and we showcase it to our customers. Then they very pleased with the outcome, and we go through the design process like that. Yeah. Hopefully it's clear. Okay. The answer to you. Yeah. 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 Yeah, sure. I'm actually hoping to establish a long-term collaboration between myself and University of Brawijaya. Yeah. So yeah, you're welcome to send to email me. Yeah. Yeah. You can search me my name on the Google, and then you can find my email address there. Very easy to find. Yeah. Okay. Yeah.
Yeah. Okay. Okay. Thank you very much, Professor Sanlam and Mr. Wahyu. Okay. Any more question from audience? Yeah. Okay. I think enough. Enough is also enough.
Yeah.
Okay. Thank you very much, Professor Sanlampung, and please give applause for Professor Sanlampung. Okay. Thank you very much again.
Yeah. Thank you. Yeah. Thanks everyone. Yeah.
Thank you, Prof.
Yes.
Oh, Rama, how are
Yeah.
you?
Good, thank you. I'm sorry, I have another meeting. Sorry. So I
No,
can.
that's fine. That's fine.
Yeah, Prof. Hopefully, this collaboration not stop until here. Maybe we can make another collaboration. Maybe join this, and maybe I will invite you as a keynote speaker. Maybe is that okay for you?
Yeah, that's fine. Yeah, hopefully we can continue our discussion because for this time I had the time only to deliver 4 of the image and processing topic, right? So I send you my material for those 4 topics, but then there are other 4 topics that the subject cover, and I'm happy to discuss and give you some. We can discuss the other topic as well. Yeah.
Pak Manca also lecture that with the interest image processing as well, Prof.
Yeah. So yeah, I'm saying I'm happy to share what I know and what I have prepared in Australia.
Okay, thank you very much, Prof. Thanks for your collaboration. Thank you very much.
Yeah. Thanks very much for inviting me, and thank you, Prachan, thank you, Rama, and thanks for everyone in the audience for spending time listening to me today and last week, and thanks also for all the students in the class. Yeah.
Thank you.
Okay.
Oh, okay, Prof. I'm sorry, I forget to share the certificate that. Oh, I'm sorry, I can't share. Sorry, maybe we can share. We can send by email the certificate. Yeah.
Yeah, sure. No worry. Yeah. Thanks very much, Rama. Yeah.
Thank you.
So see you. Have a good day, everyone.
Yeah. Thank you.
Yeah.
Have
Bye
a
bye.
nice.
Okay,
Yeah.
thank you. See you next
Bye.
time. Thank
Yeah.
you.
Bye.
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 Have a good night.
Bye. Good night. Bye bye, Rama.
Bye.
Bye
Bye.
bye, Recha. Bye.